In 2023, cybercriminals extracted $3.5 billion from enterprise networks through business email compromise. Business email compromise is a targeted cyber intrusion where attackers spoof corporate identities to authorize fraudulent wire transfers or extract sensitive internal data. Consider the recent credential harvesting campaign that hit X.com. Attackers systematically targeted prominent accounts with highly convincing fake content violation notices to steal user passwords. These attacks succeed by exploiting a structural gap in how email architecture is designed. There is a strict separation between the presentation layer, the visual text you read in your inbox, and the transport layer, which is the hidden routing data that servers use to communicate with each other. Attackers legally register lookalike domains, such as community-case.com. Because they own that specific domain, they easily set up authorized mail servers. This allows their malicious minions to successfully pass SPF, DKIM, and DMARC checks. SPF verifies the sending server's IP address, DKIM checks her tampering using cryptographic signatures, and DMARC enforces the alignment of those two policies. The transport layer authenticates perfectly, but the presentation layer is designed to deceive. The from address metadata that dictates the actual sending domain is entirely decoupled from the display name. The attacker simply types X support into the display name field, and that is what the target sees. Legacy security systems rely heavily on protocol signatures to verify a sender's intent. Because attackers mathematically pass these cryptographic checks using lookalike domains, those signatures are no longer reliable indicators of network safety. For years, phishing detection operated on fixed, recognizable patterns. Security gateways simply checked incoming sender IP addresses against global, static block lists to filter out known threats. When an IP check wasn't enough, the secondary defense relied on static keyword filters and regular expression rules. These systems scanned for specific phrases and easily caught the poor grammar and spelling mistakes typical of bulk spam campaigns. This graphic shows modern AI-driven attacks, specifically spear phishing emails and AI-generated malicious links. Attackers now deploy large language models to generate grammatically flawless, highly contextual spear phishing copy. Large language models, or LLMs, are AI algorithms trained on massive datasets to understand and generate human text. These polymorphic attacks do not just vary their text, they dynamically adapt their payload URLs and content formatting based on the specific target's browsing history, and they deploy across multiple modes of communication. A static block list hits a hard performance ceiling against this methodology. Attackers use freshly registered throwaway domains that possess no negative reputation history, rendering historical block lists blind to the threat. The shift towards semantic and polymorphic attacks dictates a necessary evolution in network defense. Stopping these threats requires moving past static rule-based gateways and deploying behavioral, multimodal machine learning architectures. To counter dynamic threats, modern AI defense systems utilize a multi-layered pipeline, analyzing an email's contents, context, and history concurrently. The first node handles natural language processing, analyzing semantic syntax to comprehend human language. Instead of hard-coded keywords, the NLP node detects manipulative tactics, like an alert claiming an account will be suspended. Concurrently, the second node deploys recurrent neural networks to track historical behavior, flagging anomalies if a user communicates with an unseen domain. This architecture is already operating at scale. Google's AI-powered phishing detection system across Gmail uses these exact layers to process massive volumes of email metadata. By combining the NLP's analysis of semantic intent with the RNN's tracking of historical behavior, the system calculates the contextual hostility of an attack, neutralizing the threat before the user ever sees the message. Text-based analysis has a critical blind spot. It cannot protect a user if a benign-looking email links out to a perfectly spoofed login page hosted on a seemingly legitimate domain. Threat intelligence platforms solve this gap by deploying automated web crawlers. These crawlers follow incoming links and fully render the destination's document object model. The document object model, or DOM, is the programming interface that browsers use to render the structural layout of a web page. Once the page is rendered, the system integrates its third defense node, convolutional neural networks. These deep learning models are optimized for processing visual imagery, performing a structural layout scan on the rendered page. The CNN isolates visual elements and logos from the suspicious site, comparing these extracted assets against known, safe cryptographic hashes of the target brand. For example, it measures the exact pixel dimensions and color grading of a spoofed PayPal logo against the authentic version. This visual analysis is the only effective defense against clone phishing, a technique where the attacker perfectly replicates the raw HTML structure to bypass code scanners. When attackers replicate the underlying code, the only detectable flaws remain in the rendered output. Sub-pixel visual analysis is therefore mandatory to identify these highly crafted, spoofed environments. This chart compares AI and traditional detection systems from the World Journal of Advanced Engineering Technology and Sciences. AI achieved 98.5% accuracy, minimizing false positives, while traditional systems capped at 85.3%. Furthermore, AI processes data in 0.5 seconds, whereas static systems need over 3 seconds. This hyper-speed processing ultimately yields massive scalability. The AI architecture handles 5,000 attacks per minute without bottlenecking network traffic or delaying legitimate communication. High computational efficiency, combined with a near-perfect accuracy rate, allows networks to shift their posture. Instead of relying on reactive quarantines, organizations can execute real-time inline blocking, effectively reversing the economic advantage previously held by attackers. However, autonomous AI systems do introduce operational risks. If detection models are trained on low-quality or unbalanced datasets, they generate false positives, quarantining legitimate business communications and disrupting workflow. Attackers are actively adapting to these defenses using adversarial machine learning. In this framework, hackers intentionally mutate their input data to mathematically trick the CNN classifier, or NLP parser, into registering a malicious payload as benign. Adversarial tactics include injecting invisible HTML characters into text to break the NLP's tokenization, or subtly perturbing a website's document object model to disrupt the CNN's visual pattern recognition without altering the page's appearance to a human. To counter adversarial mutations, defense systems require a continuous feedback loop. The AI must ingest its own misses, analyze the new evasion techniques, and dynamically update its neural weights in real time. This creates a strict requirement for hybrid architectures. Security pipelines must combine local endpoint behavioral analysis with massive cloud-based threat intelligence sharing to maintain an edge over mutating attack vectors. The presentation layer of digital communication is inherently untrustworthy. Ensuring network survival requires deploying a self-updating multimodal neural defense stack that assumes every incoming packet is dynamically hostile.